It gives me great pleasure to introduce a very special, a very young associate professor of mathematics at the Department of at Hebrew University, the Institute of Mathematics, Prof. Jake Solomon, and your talk is going to be on the Ubiquitous pi.
Yes.
Okay.
Oh, I'm sorry. Forgive me.
Jake,
You okay?
Also?
Jake, will you need the
I guess.
Less. So maybe we should move the mic out of the way because Jake is going to be using the whiteboard.
Oh.
What's a few digits?
Good fun.
First of all, to thank the organizers for inviting me to speak here.
maybe the microphone.
Speak with the
I
microphone.
just have to press it.
It's better?
Much better, yeah.
Okay. So, well, just wanted to say some sort of well-known things about pi, but still let me.
Whoa. Here it goes.
Here again.
Now we want to copy the mic.
Say that again?
Now we want to copy the mic.
Maybe. They can hold it for it. I'll just try to speak louder. Okay, well, I'm going to just repeat some things which were said a little bit quicker before. So, pi is usually defined as, well, there's different ways of defining it, but one way of saying it is that it's like got something to do with the ratio of the, so if you have a circle, so you look at its circumference, of the circle, then it's going to be equal to 2 pi times its radius. Or sometimes we'll say the area of a circle will be pi times its radius squared. Different ways of saying what pi is. So this presupposes that we understand what a circle is, but there's kind of, if you want to say what a circle is, there's different ways of saying what it is. One I particularly like is kind of implicit in the following. I should just move this over a little bit.
Should we just move it up?
Yeah. At some point, maybe I'll screen that, but
Yeah, the area that's covered is not used for the. It's fine.
okay,
it's
great.
fine.
It's good.
It's not
Great.
bad.
So there's something called I said we're going to talk about ubiquitous pi because there's a lot of places where pi shows up in math and physics, and so just mention some of them. Well, so one thing so my research interest is in geometry, and I think one of the sort of oldest problems in geometry was to sort of definitely goes back to the ancient Greeks, was the following kind of statement. To try to justify the following statement, took thousands of years for people to figure out how to do this. It sounds almost, well, let me write it down. So suppose you have a, is this visible or should I go back to the top of the board?
That's fine.
People sitting in the back.
It's good.
So if I have like a curve, let's call it C, and then I can look at a closed curve, and then I can look at the area. I can look at the area. Well, I can look at the area enclosed by the curve, and let's call this, so so look at the area. Okay, we'll call it A. So A is going to be the area enclosed by C, and L is going to be the length of C. So you could ask, if I have, a certain length of fence, and I want to enclose the biggest field possible, how should I do it? What are the limitations of a given fence? So the isoperimetric inequality states that, well, if you take the area and you compare it to the length squared, so it only has to be less than or equal to the length squared over 4 pi. Okay, so that's the isoperimetric inequality. Goes back, I guess it was maybe thought of by the ancient Greeks, but not really proved until not so long ago. And so just for example, so you could take, for example, C to be a square. So you have sides of length 1. Then you would have well, the area of a square, side length 1 is 1, and the length of the curve surrounding the square is 4. You have 4 sides. And if you look at, you have A is 1, and if you look at L squared divided by 4 pi, that's 16 over 4 pi, which is, pi is a little bit less than, it's like a little bit more than 3, a bit less than 4, so this is definitely going to be less than, it's going to be greater than 1, because this is a little bit less than 16.
It's 4 over pi.
Okay, that's also 4 over pi.
If
This
it's
is
equal
definitely
to
greater
it, it is
than
less
1.
than or equal to it.
Right? So this is an example, and of course the best example is when you take C to be a circle, and you have a circle radius 1, the circumference will be 2 pi. So you have A going to be pi r squared, pi, L will be the circumference, that's 2 pi r, 2 pi. And then you take L squared over 4 pi, that's equal to
4 pi squared over 4 pi, which is pi.
4 pi squared over 4 pi, which is equal to pi, which is exactly equal to A. So in this case, instead of having inequality, you have exactly inequality. And a famous theorem, which was proved, maybe not so long ago, was that that sort of the unique way of surrounding the most area with given length of fence is by taking a circle, and here you see it. You see that certainly this inequality is satisfied with the circle, and you have to prove that no other shape can possibly do better than this. So it's a kind of a surprising. Well, I mean, surprising you can actually get your hands on such a thing. That's a way of thinking about pi. Even if you don't know what a circle is, you can state this inequality and kind of say what pi is. So that's one place where pi shows up. There's a lot of ways that pi shows up. So one of the sort of most well-known expressions for pi is this one. So it says, well, you start with, so you can do 1 minus 1/3 plus 1/5 minus 1/7, etc. And this will give you pi over 4. You can multiply by 4. Then there's another sort of formula which is even sort of, this one, let's say, there's a similar formula which is a bit better for computing things, and it also relates to number theory. So you can say the following thing, that this is equal to just 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, and so on and so forth, okay? So this is what people call the zeta function evaluated at 2. So the zeta function was, I guess, attributed to Riemann. It's the subject of one of the most famous open questions in mathematics, the Riemann hypothesis. So, in general, zeta of some number, let's say zeta of x, is defined to be the sum. So, let me just write it out without interpretation. It's going to just be sort of 1 plus 1 over 2 to the x plus 1 over 3 to the x plus 1 over 4 to the x, etc. Okay? And it turns out that if you evaluate this function at 2, then you get this number which is very close to it. It's just pi squared over 6. And so this is sort of, I think, if you want to see an infinite sum which kind of converges, this is sort of the first sum I teach in the calculus class sometime. Trying to think of some example of a sum that you can show that it converges very easily, but it's really hard to say. That you know what the limit is, it just converges to 1. But if you're looking for a sum, which it's very easy to show that it converges to something, but it's kind of very mysterious what that something is, I came up with this one as the easiest one to write down. I mean, that's not a statement. So, and sort of, you take these kind of random sequences, and they tend to converge to something which has to do with, oftentimes they converge to something that has to do with pi. Well, that's, let's see.
You proved this one?
This one, I think this one was proved by Euler. Yeah.
This is the basal problem.
Yeah.
Problem that made his career.
Interesting.
There's similar results of X is an even integer.
Right. So for any
four,
even integer.
For odd integers, it's unsolved. And for numbers less than 1, we can cheat.
Okay. So so other places where pi comes up. So I was asked to throw in something about physics here. So there's the first thing which comes to mind is the Heisenberg uncertainty principle. So states that this is kind of one of the foundation cornerstones of quantum mechanics is that if you have, say, some particle and you try to measure its position, you also try to measure its momentum, you can never quite pin them both down at the same time. So if we say, let's say, delta Q is the uncertainty in the measurement of the position. So it's like let's say I have some particle trying to pin down an electron, and you're trying to measure its position. So it's jumping around in some quantum mechanical way, and so you can maybe nail it down inside of some little box which has side length delta Q, and then you have delta P is the uncertainty in the position in the momentum. So then the uncertainty principle says that actually we take the product of delta P and delta Q, then it has to be greater than or equal to h squared over 4 pi. Okay, so h squared is the Planck constant, which is something which it's a number, but it also has some kind of like intrinsic physical meaning, and in order to convert that into the thing which is relevant for the uncertainty principle, you have to multiply by 1 over 4 pi. So what is h? So h is it's the so if you have a photon and you want to know the energy of a photon, so that's equal to h times the frequency of the associated electromagnetic radiation. So, for example, if we looked at a photon of visible light, so this frequency might be something like so for visible light, not say infrared or ultraviolet or radio waves, this is something between roughly 4 and 700 terahertz. Okay, so that means, I guess, trillions, hundreds of trillions of alternations per second. So you can imagine this h here is extremely tiny. So the energy of a photon, even of is going to be really, really tiny. And you take it, multiply h by some enormous frequency, you still get something tiny. So h is really, really tiny, and so you generally don't observe this inequality in everyday life, but nonetheless, it involves pi, and it's extremely important in physics. Okay.
Never know where they are.
So,
Well, we could know where they are if we had absolutely no clue how fast they were moving.
so it's roughly speaking 6.62 times 10 to the negative 34 meters squared kilogram per second. So, just for the record, right. And actually, in physics, usually people work with h bar. So this is h, not h squared. H bar is
H over 2 pi.
times the h over 2 pi, because there's this kind of pi which comes up all over the place. It's more convenient to just divide by it once and for all and then forget about it. So physics students often don't even. I don't think I remembered this being there. Though I did study physics at some point. Anyway, there's a lot of mention of E here, so I thought I should say something about E, especially since you need E to spell pi, in the sense that you eat. Definitely think of. when I first learned about E was I wondered kind of how much interest I would make if let's say I had suppose I have 100% interest.
You can just give the convergent series definition. That's a lot simpler.
Yeah, but I think this one is kind of somehow more interesting because convergent series doesn't mean much. At least didn't mean much to me. At least until you learn calculus. But somehow this, we have 100% interest per year.
It's also calculus, though.
Well,
You're still taking the limit.
it's a little more intuitive if you ask me, but 100% interest per year, and you kind of.
Convergent series are also taking the limits.
So if you want to take, so what you could do is you could ask, what happens if, instead of just giving 100% interest at the end of the year, you say, well, every month you give me 100 divided by 12, 1/12. So this means you add a whole times the original capital at the end of the year. So suppose instead, so you could do like, just, after, so compounding once a year. This will give you kind of, so like, if you have $1 at the beginning of the year, so at the end of the year you have 2.
8.33% interest is a 12.
But if you do it, say, once per month,
At 8.33%.
but now that means, you have to, of course, take it proportionally less. So that means that you kind of do, so this would be kind of like 1 times, 1 plus 1, right? But you could do instead, sort of once per month would be sort of, well, you take your initial amount, but then you sort of multiply it by 1 plus 1/12. That's how much you get in 1 month, times a bunch of times, right? So, this, 12 times, or in short, that would be 1 plus 1/12 to the 12. Okay, and you could do it once per day. And then you'd get 1 plus 1/365.
And a quarter.
365. Let's be imprecise. For the purposes of
0.24.
just like the something like line stuff like something was it?
Jewish calendar works with 365 1/4, taking that into account.
So
If you're using halacha, you need to be more precise.
so this is an approximation. So of course, then of course you could try taking this larger and larger, and eventually, as this number gets closer and closer to E, which is roughly 2.718.
2818,
And
2845.
goes on to many, many things. It's on the computer, but about 1,000 of them, but can't remember
I
that.
have 16 digits.
So, and then, your name is Yitzchak?
Yeah.
So, I think Yitzchak was asking me to write down the series of, infinite series approximation. So one way of saying this would be like this. So take 1 plus 1/2 plus 1/2 times 3 plus 1/2 times 3 times 4 plus 1/2 times 3 times 4 times 5, so on and so forth. That will be another way of saying E. Now what does E have to do with pi?
Well, e to the pi minus pi is almost exactly 20.
Yeah. That's
Maybe you want to say something.
That's a well-known, completely irrelevant math fact.
funny thing. Was not aware of that. So
Are you missing a term there?
So I just wanted to mention sort of a different place in mathematics where pi appears, which also involves e, but which is not maybe the first thing you think of with e and pi. So it has to do with probability. So a very simple statement of what's called the central limit theorem, which is one of the cornerstones of probability. So this is the central limit theorem is much more general than this. But one small consequence is the following thing. Suppose I play a game where I toss a coin, n times, so n is a number, and if I get heads, I make $1. If I get tails, I lose $1. Okay, so then let's call xn is going to be, my total gains or losses considered as a signed number after the game. All right, so then a good approximation for the probability that let's suppose that A and B are two numbers, so two numbers somewhere between negative infinity and plus infinity, and the probability that square root of n times A is less than xn is less than square root of n times b is very closely approximate, depending on, as n gets larger and larger. Well, it's closely approximated by a certain picture. Let me draw for you.
X is the sum of dollars, or is this the count of times?
So xn is going to be sort of like your total gains or losses. So if you say had 4 flips of the coin and you won 3 times and you lost once, you would have x4 would be 2, because you gained 3 and you lost 1, so in total you have 2. So example, let's say toss 4 times, so that's n equals 4, and you say 3 heads, 1 tail, 1 tails.
So xn is always even.
So then that's sorry.
But it has to be
Never mind. Never mind.
Xn will be 3 minus 1 equals 2. That's how much you have at the end of the game, right? So then you go over all the different possibilities and start graphing and seeing which ones are more frequent, which ones are more common. Of course, usually you expect to get 0 because you have equal chances for winning and losing. But sometimes, you might get more one way or the other. And the probability of getting between square root of n, so between this example, square root of 4 is 2, between 2a and 2b is going to be, this probability is going to be the area under what people call the bell curve, between A and B. Draw a little picture of that. So we draw it up here. is you have this is a x, and this is going to be y, and we can look at the bell curve. We'll get to why this has got something to do with pi in a minute. Or Gaussian, that's right. And so if you look at, say, A here and say B over here, and you want to know the probability of getting between square root of NA and square root of NB, it's going to be closely approximated by the area between A and B under this Gaussian. And so this area. Okay? And now for the main point of going to this digression was that the equation for this curve involves pi. So this curve is y is equal to e to the minus x squared over 2 divided by square root of 2 pi. Okay? So here you have a formula which involves both e and pi, which is kind of a cornerstone of probability theory. But how much time?
Which time do you need?
Well,
Right.
I mean, I have little subjects I can talk about. I mean, I don't want to go on too long.
How does the audience feel?
About 15 minutes?
Okay. So, I think in 15 minutes, I can explain how you can calculate pi at home. Otherwise, in other words, Archimedes' method, which was very, which I think was very much in the spirit of the song we just heard, the most enjoyable music.
Before you go on to it, can you mention two things? Euler's formula, which ties E and pi together. So Richard Feynman said it was the most beautiful formula in mathematics.
Okay, so that's another possibility.
And the second thing is, maybe you can say a remark why these things are happening. What do infinite series have to do with a circle, for example? It's really
I actually know a very elegant proof of that, but it takes quite a bit of time and some lampposts.
okay, but there must be, there should be some explanation why pi pops up everywhere.
Feynman is so great.
Yeah,
I'd
well,
love
that
to hear
would-
about
well,
Feynman.
I think
I'd love to hear about
the
Feynman.
basic answer to all of the question is that in all these situations, there are circles which appear.
How do circles appear in an infinite series?
You know
So-
the proof of the Basel problem using light and lampposts in a circle?
I do not know that proof, but I would do it using complex analysis. And the basis for that would be basically the Cauchy integral formula, which eventually involves somehow the circumference of a circle.
Very quick summary of the way to prove it using lampposts. The distant,
Maybe
no,
we're better to go this.
At the end.
Later on.
Yeah, we'll do
like
it.
15,
Yeah.
no, like 10 second summary, not the actual thing.
Later on.
Okay.
But again, how does pi or circles fit in with infinite series?
So
Also with E, by the way. What does infinite series have to do with E?
so
But they do.
maybe
Maybe this is getting a little.
let me try to say something about
If you want to use
Well,
the
this pi is infinite, E is infinite, and the infinite series are infinite, so it goes well together, you know?
okay, let me try to say something about what it means to be a transcendental number. I mean, I guess it was mentioned many times in the lectures, but I think this is all sort of converging to that point. Excuse the pun. So there's like a hierarchy of different numbers. It's like there's whole numbers. So I'm going to be sort of historically very, very brief and just pretend the whole numbers start with 0, 0, 1, 2, 3, right? And then you're going to have also, like, there's, signed numbers, like positive whole numbers. So there's signed numbers. They're like -1, -2, etc. 0, 1, 2. Okay? And then there's what we'll call rational numbers. This would call, I would say, integers. That would be the technical term for mathematics. This would be natural numbers. And here we have rational numbers.
You have a zero there in the natural numbers.
Some people define natural numbers to include zero. It's a question of custom. And there's rational numbers, of course, which are sort of like fractions. Like so, you have it's a little bit harder to draw them because you have something like 0, and then
So A over D, where A and B are
1/2, 1/3, 1/4, and then you have 1, 2, like you have 2 over 1, 2 over 2. Sum this up, right? This should be 1. Then 2, 3. We have 2 over 2, 2 over 3, 2 over 4, 3 over 2, 3 over 3, 3 over 4, etc. So you have like, I mean, there's a lot of them because you have to have the denominator and the numerator. These are so fractions basically, or improper fractions. But of course, you have also negative ones too. 0, minus 1, whatever.
plus or minus.
Yeah, plus or minus. Improper fractions, probably. Same. Then after that, you can have real numbers. So sort of all things which can get, these are like things which can be approached by fractions, but maybe never actually realized as a fraction. So inside of these we have, of course, there's the rational, there's also the irrational. So those are the ones which, certainly all rational numbers can be approached by rational numbers. These are rational numbers. We also have the irrational numbers. So these are the ones that when you write them in decimal expansion, the decimal expansion never repeats and it never has any kind of pattern, right? So it never repeats itself, let's say. It goes on forever, right? Okay, and then sort of inside of these, well, maybe I should say between the real numbers and the rational numbers is also the algebraic numbers. There's certainly real numbers, but they could be something like also numbers which solve some kind of algebraic equation. For example, like the square root of 2. So this is going to be an irrational number, so it's not rational, but it is going to be a real number. Okay. And so it's okay, and the idea is that so it's pretty easy to talk about whole numbers or integers or rational numbers. You can always just write down such a thing. You can talk about algebraic numbers. You just say they satisfy some equation. So this x squared is equal to 2. That will give you the square root of 2. Right? So that's an algebraic equation which is satisfied by the square root of 2. Then the thing is that sitting inside of here, so pi is, and so there's also the transcendental numbers here. Okay, so these are the ones which are not algebraic. So that means that there's no equation you can write for pi, for example. So pi,
No polynomial equation.
no
rational
equation
polynomial.
which involves multiplication, addition,
No
subtraction.
rational polynomial. Otherwise, you could have x minus pi equals 0.
Right. So in other words, so you can never, if you write something like a times pi plus, so let's say a plus pi times b plus c times pi squared plus d times pi to the cubed, and so on and so forth. As long as you want, no matter what a, b, and c are, as long as they are the a, b, c, d, etc. are all rational. Okay, so then this will never equal to 0, unless, and they're not. I mean, I have to assume that one of them is not 0. Okay, that's what it means to be transcendental. There's no way you could write some equation involving only this kind of an expression, which will equal to 0. Okay, and there's sort of what's responsible for letting us see this is that you have the real numbers so this is actually really hard to prove. It took until 1882 to prove this. So real numbers sit inside of complex numbers. Okay, and complex numbers, so you could say when we went from natural to integers, we kind of added negative numbers. Negative numbers is the kind of things you don't necessarily bump into walking down the street, but you kind of sort of say they're convenient for math calculations, and you sort of just throw them in, and then you kind of find them everywhere.
Usually you do recycle.
Okay.
Negative numbers, thank you.
Yeah, so it's hard. With bank accounts it's easy to run into that. And then there's rational numbers.
Forces moving in opposite directions.
This is kind of an abstraction, right? So I mean.
Uneven meters.
Okay, so you basically. So the thing about real numbers is that you can ask, if you have a negative real number and you take it times itself, it gives you a positive one. If you have a positive real number, you take it times itself, it also gives you a positive one. Can you ever have a number which, when you take it times itself, it gives you -1? So you just add, add negatives. So a similar kind of procedure that you kind of just formally add these numbers that you want gets you from real numbers. Here you add something which you add I, right? And I satisfies this equation. I squared equals -1. Okay? And you allow all possible combinations of I and other numbers, and you can calculate with these things naturally. So then complex numbers are all things of the form x plus iy, where x and y are real numbers. Okay, so and then you can multiply these guys just like they were numbers, and all you have to remember is that I squared equals -1. The thing is that it's convenient to draw complex numbers, and we're going back to why somehow all these things have pi in them. How is it that this kind of circle shows up in all these different seemingly unrelated places? It comes down to the fact that, well, one way of thinking about it is that complex numbers, you can write them, it's very convenient to visualize them as sitting in a plane. So x and y, I didn't choose them randomly. They're supposed to be the x and y coordinates of a plane. So as you draw the real numbers on a line, you draw the complex numbers in a plane. So you have the complex plane. You have sort of x here and iy here. And of course in the plane you can talk about a circle. And so it was mentioned that there's this formula of Euler which says that e to the I pi plus 1 equals 0, because this is kind of all the numbers which just which exist kind of their own right. Like e, you can't get along without it, and pi, you can't get along without it, and 1, also you can't get along without it, and 0, 2. And so you have them all kind of included in one beautiful
gamma?
formula. You can probably get along without.
It's very offensive to gamma.
Sorry about that. So, I was just going to try to explain kind of geometrically what this means, because it's a little bit strange. I mean, to see some number to a power which involves this imaginary number. So how can you possibly try to envision this geometrically? So the thing is that if you have a function of a complex number, if you have some way of taking one complex number, so let's say this is the complex, so this is the complex numbers. Okay, and you have a way of taking this and getting another complex number. So, you know, right, so it's going to give you some kind of perhaps complicated way of mapping the complex plane to itself. Okay, and sort of the one which we're interested in for the purpose of understanding this formula is, of course, the one that takes, you know, f of f of z is equal to e to the z. Okay, so think z is equal to x plus iy. This will be e to the x plus iy, which by the usual rules of exponentiating, e to the x times e to the iy. So if you take something times itself x times, then you take it times itself iy times. That should be, you know, the same as taking it e to the x plus iy times, right? So, so if we draw, so I mean, there's a basic fact about functions which can be written like this, where it's some kind of standard operation which you do with numbers, and you just do it with a complex number. I'm not going to go into the, you know, details of that definition, but more or less any function you can think of for real numbers, when you write it down for complex numbers, it's going to satisfy a really cool property, which is that it's conformal. So, which means it preserves angles. Okay? So I'm going to show what E does. So, this is a very general thing about, if you put it in the right language, it's even not very hard to show, but I don't have time to do that. So here go Z goes to E to the Z. Okay, so we can look at, I hope that some of these colors work. Just really should these colors work. Yeah, that works. So you can look at these lines. These are the X lines, parallel to the X-axis. So let me draw again the X-axis. And so I'm going to do this IY. Okay. And you can draw these lines. And it's not very hard to see that the X-axis, the lines parallel to...
wrong marker.
the lines parallel to the x-axis, they happen, it's pretty easy to see this just from this fact that this holds, right? So, so these lines get sent to these lines. Okay? And, well, you know that the thing preserves angles. So now, if the horizontal lines get sent to the radial lines, then what must the green lines get sent to?
Circle.
They have to get sent to circles, because circles are the only things which are at right angles. So the green lines and the blue lines are at right angles, right? So if we draw here, the angle between the green lines and the blue lines is always at right angles, no matter where you are, right? So now if we draw lines in this plane, which are at right angles to the radial lines, we're gonna, so here, so you can see in this picture that the angle is preserved. Okay? So now once you see that the green lines go to a circle, it just takes a little bit more work to see, if you remember this formula from calculus, that d to the z, e to the z is equal to e to the z. You can easily figure out that you go around these circles. So if you take the circle at radius 1, so you can see that you're going to be going around it at unit speed. So it turns out that to go around the whole circle, you have to move up. Of course, the circumference of this circle is 2 pi. So in order to move up by, let's say, so this is over here is -1, right? -1. To go halfway around the circle, you have to exactly move 2 pi along this curve, which means moving 2 pi. Sorry, pi along this curve, right? So you can start from here and go up to, let's say, pi, right? And if we take that little segment, it's going to be wrapped around here, from here, all the way over to here. Okay, so this point here is exactly, okay, so e to the 0 is 1, so it's called, this will be 0. I didn't draw it exactly, this is going to be 0. Okay, so this point here is just I pi. Okay, so this point here is I pi. And that means that when you take e to the I pi, it gets mapped to -1. So this says e to the I pi is equal to -1, and that means that e to the I pi plus 1 is equal to 0, which is Euler's formula. It's kind of a geometric explanation, and I think most of the, these infinite series that give you pi or pi squared over 6, eventually they all get expressed in terms of complex numbers. That's one way of dealing with them. And eventually, to evaluate them, you have to look at sort of the circumference of the circle and the plane, just like this circle that I was drawing. So I think that would be sort of the most coherent explanation I can find for why pi pops up in all the different places. Same thing, for example, for the bell curve. Why does it show up in the formula for the bell curve? Again, it comes down to that. Many other things too, like also, for example, through that it gets into the Heisenberg uncertainty principle. And I think that's probably going to listen to someone.
Okay, wow.
Is there going to be a test?
Prof, there was really something. I must tell you, I always knew that at Hebrew U, the medical and the dental faculties were like world class. But having you as a professor in the mathematics department, I can really understand why Hebrew University is one of the top 100 universities in the world. Really, it's been an honor and a privilege to hear It sounded a bit like Greek to me for all of us non-mathematicians, but it really, it's unbelievable. It really is very special, and thank you. Your presentation was remarkable, it was riveting, it's amazing. And really thank you for outstanding presentation.